Hello community, so great that you are back. Today we talk a little bit about reasoning complexities, no? So imagine you have a little ant here on a Möbius strip and this little ant is searching for a solution. Let's say we have a reasoning query. Now, either you can add now a dimension to the state space of the system, or option 2, you can add 5 more linear steps for this ant here to walk on this Möbius strip. What is the better solution? If you want, just imagine the ant is allowed to go 7 steps here on a Möbius strip, or if you want here, take a climb bottle if you want to get a little bit more complicated. But what is better? Add dimensionality to the state space, or just allow to ant to search here more steps, a multi-step reasoning. So this, of course, transfers here to a complex query that we have. And then we simply ask, hey, is it better to have a high-dimensional search space or a high-dimensional large language model? Or should we go here for a multi-step reasoning model? So train it for dimensionality or train it here for multi-step reasoning. And I just don't want to limit ourselves to the state space. Go for a higher dimensional feature vector, go for a higher embedding vector. Whatever you like, it is more or less, doesn't really depend here on which particular state we go in higher dimension, but just think about it. And now, you know what? We change it. From an ant, we go now to a spider. And spider have a very particular property, no? Yes, exactly. What is your answer now in this particular case? You have 2 options. No? You can add a dimension to the state space, or you can allow the spider now to add 5 more linear steps on the Möbius strip. What is better now if we have suddenly here on our topology an object like a spider who can just use shortcuts? And shortcuts will be the topic here at the end of my video again. So simple topology or use a climb bottle. Think about it. What model would you choose? Now, of course, yes, of course, if you know, there is another constraint in our system because we do this here on planet Earth. So we do have gravity. So this spider here needs another boundary condition to work and have here and develop those higher dimensionality shortcuts for its reasoning. So to solve now a complex reasoning task let's go with a large language model, and now we look here in particular at test time compute scaling. So what we need? Do we need a higher dimensional space, a higher dimensional latent space, higher dimensional embedding, higher dimensional feature vectors, higher dimensional hidden layers for the more complex task? Or do we need something completely different? Do we need to provide the training data sets here for more multi-step reasoning training? And it is a complete different video if we just will focus here on supervised fine-tuning and or reinforcement learning. So staying here in a lower dimensional space like a Möbius strip, but providing here more step freedom given more complex tasks. What would you choose? Now it is rather easy and we have a beautiful new study. And in general, we can say our LLMs can generate and use additional test time compute tokens to perform unseen and challenging reasoning tasks. And you know this, no? O1 or O3 from OpenAI or from DeepSeek, R1, those are our reasoning models. But despite their empirical success, they really work. For us in research, it remains unclear in what way these additional test time reasoning tokens contribute to the improved reasoning performance. We have no idea how it works. Now, existing literature generally associate here the need for more reasoning token with kind of a harder to solve problems. But is this true? And yesterday was a new study published here, Cornell University and Howard University, and they went one step further to come to a solution. The authors tell us we demonstrated across diverse tasks and different LLMs, there exists an amount of reasoning tokens at which the task accuracy peaks. So we do have here an optimum. And they say we refer to this quantity as the critical length. And it varies given task and mode. But because, of course, the task complexity in itself, given here lingual topics, is real hard to measure. How you want to measure this? So they say, hey, we need a mathematical framework to approximate the complexity question. No? So they tell us, hey, we propose a framework based on the fact that many tasks can be represented here with a mathematical simple model, a deterministic finite automata model. And they argue by formalizing now the reasoning complexity through this lens of a simplified DFA, our results now offer practical insight into how LLMs utilize additional reasoning steps at inference time, test time, compute scaling. Because they come up now with the idea that the critical length, they can kind of predict with a linear regression model from the properties of the underlying DFA, we can perform rejection sampling to include only those answers that are at the correct critical length and improve the performance of the reasoning of those LLMs. Now, you know, this is not new because look at this from February 2025, Peking University, MIT, and TU Munich, they had a similar idea. Understanding the chain of thought length in LLMs when more is less. And they found out that as the number of the reasoning steps increase, the performance initially improves, but then it starts to decrease. So again, there is here a discontinuity here, slowly improvement, but also more is not always better. So let's open up this video if you have these basic ideas now together, and let's have a look. So our DFA framework that formally quantifies now the task difficulty and reasoning complexity will allow us here to some deeper insight, and this formalism, if you want, will enable us to study a broader range of reasoning tasks. And now finally we can go beyond mathematics, because if you look at my videos of the last weeks, there was a strong focus on mathematics because mathematics was so easy. No? Either it's a correct result or an incorrect result. With language, you know, you could say, oh, I could interpret this result as maybe referring to. And now we have another mathematical approximation, simplification, but we can go beyond mathematics. And this is beautiful. Now, you do remember this study here, the illusion of state in the state space models, in the Mamba model and the S4 models. This is here from March 2025. And they answered here the question, do here the state space models truly have an advantage over our autoregressive transformer model in the expressive power for state tracking? For state tracking, please, only. And they found the answer is no. And they even found that the member struggles here with the state tracking. Now, if you're not familiar with state tracking, I would recommend here this paper for you. This is from April 2024. Yes, I know it's more than a year old, but it's a good paper, and it shows you here the LLM state, an open world state representation for long horizon task planning with LLMs. And they give you here this. And this is so nice. I always come back to this. So they say decision making. How does it work? We have an LLM as the attention, an LLM as the state estimator, an LLM as a policy. And they tell you start here simple, no, with an input. You look around as I don't know, a robot, and then you find here, okay, what I can identify all the objects in the room, and then I have a task description, a goal. No? The LLM as attention is simple. I have a generated object map. I have milk, 0, fridge, 0, whatever. And then if I have now the input here, milk and fridge, and the action now taken for a particular task is pick up the milk, open the microwave, place in the milk in the microwave, close the microwave, switch on the microwave, and wait till it is successfully heated. You see, then we have a new state of the system, no? Because now the output generated a new state where the milk is now in a heated state and it is positioned in the microwave and the fridge is open. So it is that simple. And the policy is just the plan as I showed you. So you see, you can simplify so much if you just read the right paper. Talking about the right paper, I would recommend this from February 2025, State Tracking and Reasoning for Acting and Planning with LLMs, Imperial College London Department of Computing. They say at the core of their methodology, and they call it the chain of states here, there's a straightforward annotation of the few short examples with the goal traces, the state traces, and the reasoning traces. So you see, from a simple reasoning trace, if we want to have the system have a higher performance, now this, what they propose here, this chain of state methodology, where they have the reasoning traces, but also the goal traces, how much of the goal did we already achieved, and the state traces. Where's the milk currently in this particular step when we went, I don't know, 46% through the complete flow? Interesting that now we track and we log those properties of a system. Now, this is now a very interesting study here from March 2025. This is from Key Laboratory of High Confidence Software Technology, China School of Computer Science, Peking University, University of Hong Kong, and Shanghai AI Lab. And they have now a finite state automata inside the transformer with a chain of sort. And this is now a mechanistic study of state tracking. So you want to pierce inside here of our transformer that has a chain of sort training for this, if you want, inference generation of the reasoning traces, of the more complex reasoning traces. And you know what? Inside the transformer, we find a simpler mathematical model, a finite state automata. If you're not really familiar with this, never mind. If you are, skip the next 2 minutes. So they say now here, there's a limited mechanistic understanding of the algorithms that how does the transformer architecture that is now trained on a chain of sort can learn? How is this possible? We want to understand what's happening inside the transformer. And they provide here evidence of an implicit finite state automaton. Automaton the single. And they say we find evidence of an implicit FSA, and finite state automaton, within the transformer model, where each state is compressed by a distinct set of neurons. Now this is interesting. So we try not to solve the complete complexity of the transformer architecture for this particular topic, but we say, you know what? Within the transformer, we identify easier mathematical models that we can solve rather easy. So why not focus here on the simplified models, solve them in the easy solving space, and then we can come back and look at a more complex system. And that's what we're going to do. They start here with the cyclic group of order 2. So, mathematically, 2 elements often represented as 0 and 1, and the operation is an addition modulo 2, equivalent to the XOR operation. So this system has 2 states, Q1 and Q0. And now we can define rules, transition rules here. They look like this, 1, 2, 3, 4. So if the system is in the state Q0 and the input is M0 occurs to the system, stay in the state Q0, and then you just have some rule-based instruction. Those are the transition rule to move here to different states. And they give us here this beautiful visualization, and they say, look, if we have the transition rules that I just showed you, and we have the 2 states, Q0 and Q1 of the system, and here the different input, M1 to whatever, and we have here a normal transformer architecture where we have our attention, self-attention, and our multi-layer perceptron in multiple layers, and then the output is simply then a state Q hat, for example. You know what? We can, if we train this transformer sequence with our transition rules, so chain of sort training, the train box shows how the model is trained, doesn't just predict the final state, it's trained to generate the intermediate step by step. This means the chain of sort. So this forces now the model, our transformer, to explicitly track the state transition. And this is happening inside the transformer. And because this is a capability of the transformer, we can recover here our FSA, our simpler model. And the central claim of this paper, the authors, is after being trained here, the transformer with a chain of sort on data generated here by the Z2 transition rules, the transformer learns an internal mechanism that effectively stimulates or recovers here the FSA. So this is now really nice if we see that this works. But how does it work? And the authors, please read the paper, they have a detailed analysis. The videos here, I'm not focusing this, I just need the fact that it is in there. there's an FSA in our transformer architecture in a simplification for a mathematical understanding. They went, we investigated how the transformer does this, and they find the evidence that specific neurons within the multilayer perceptron, particularly the later one, become specialized. So they can now have one distinct set of neurons tends to activate when the system is supposed to be in a state Q0, and another set of neurons is activated when the system is supposed to be in a state Q1. So you see this here in the green dot, if you want, and in the yellow or orange dot. So if you really look here at the output MLP neurons, they are now showing us clearly there is really this as FSA inside. So by activating these different neuron sets, the model can represent and differentiate these two states internally, allowing it to correctly apply the transition rule for the next step. So this means we have here now a simpler mathematical model. We don't have to go through the complexity of a transformer that we do not understand at all in complete details, but we have now an FSA model that will help us in a simplified version. So here, after training on the data generated by the transition rules here of set 2, the transformer and the chain of thought successfully covered an implicit FSA by differentiating two states, the green one and the orange one, of set 2 using two distinct sets of neurons in the late layer, multi-layer perceptrons. So what we achieved? Take a step back. Transformer trained with a chain of thought. This is exactly what we did, for a state tracking task. Don't just learn here the surface patterns here, but they actually build an internal representation. And this internal representation is what we are interested in. How do you do this? How does it look like? And we find out that this is an implicit FSA. This is our finite state automata. And this is here of the underlying state transition rules built. And this representation is now mechanistically linked to the activation patterns of our neurons in the neural network, specifically here in the late layer multi-layer perceptron neurons. So you see, all of this just to tell you, I think it's okay that we can have here the logic built up on the FSA complexity. I ask here ChatGPT to provide you a simple FSA example here. There is it, but you just need to understand this simple FSA clearly demonstrates how a machine with a limited number of states can really track here a property. And here in this example, it's the parity of the zeros by transitioning between the state according to given fixed rules, the transition rules. So we do have this track property enabled here with a simple FSA. Great, so that we have the elements, now we can start to cook here. Now we just need a spark of genius and then we go. And there's a critical length. The authors here from Harvard tell us LLMs have an optimal thinking length. Now this is interesting. And they looked at all the different models. Look, they looked at the Q1, the 7B, the Llama 8B, the DeepSeek, the version 3, the Mistral 8B, the GPT-4 Omni, the O3 Mini, and then all the distilled R1 models from the Q1 and from the Llama model. And you see the provider, you see the size, and then you see here the last column refers you to the model's final reinforcement learning training stage. Either it was instruction tuning like on these models, or it was what we are looking for, chain of thought reinforcement learning. So let's have a look at this model and let's see what is the optimal thinking length for chain of thought reasoning. Now, what data do we use? What benchmark do we use? Now, they go here to published data that are famous here by Google Research and Stanford University from 2022, the Big Bench task, or here, if you want a little bit more recent from January 2024, MIT and Meta AI here, Crooks evaluation. But never mind, they find, you see here, Crooks evaluation, all the different tasks, whatever benchmark you take, there is a critical length. And you see this here. There is here, if you want the accuracy, the reasoning accuracy improves, then there is here really a threshold. And then, even if you provide more token to the reasoning, the performance goes down. And you see this, up, 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 and then performance goes down, up, 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 performance goes down, up, 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 performance goes down. You see it. Now, what's interesting, just a personal remark, this is not really a steep change. No, so you see here, for example, on those tasks, it is barely noticeable that there is now a slight decline in the linear slope. But okay, some other models, as you see here, wow, chuck, and then saturation. So there is something happening here, this critical length, we call it L star. And they say, we looked at all the different models, no? And all the different models have this L star, clearly identifier, sequence length, normalized and whatever. So we do have an optimal sinking length in the TTS, in the test time training. If you look now at all the different models, you see the critical length varies by each and every model. Here, this is the critical length indicator. Okay, so you see generation length from 0 to 4,000 tokens. There are the differences. Beautiful. But it also shows us that there are places where more reasoning tokens are correlated with worse accuracy. So more is not always better. You just have to find the sweet spot of the length. How is this possible? Now we come to the core idea. The optimal reasoning length here of test time compute relates with the DFA run length. And you say, now we make the interconnect between the automata theory, the simplified mathematical theory, and what we really can use here when we use here LLM reasoning length. So, this answers now the question, if you want, what controls here the critical length of a reasoning token in test time compute? What is the most important factor? Now they said, hey, this is now interesting. Now we have a benchmark of reasoning tasks can be represented as the deterministic finite automata, the DFAs, and the language of the DFA provide an explicit, measurable dimension with which to characterize complexity. So this is exactly what we were looking for. I told you complexity. What is complexity? How do you really define the different dimension? And if you want inherent complexities in the complexity itself, now they say if we use here this mathematical simplification of a deterministic finite automata theory in mathematics, we can find now measurable dimensions that characterize the complexity. Not completely define them, but hopefully characterize them to, 80, 90%. All the tasks we consider can be represented as DFAs, where one way to solve the task is to implicitly infer a DFA and then transverse its states. If you want to see this in the official mathematical notation by Stanford, this is it. Cornell and Stanford, this is it. If you like this one, or just go here with my examples. Here, another example to show you explicitly what is the run length. So we say here, consider the problem of evaluating the parity of a bit string. This is here 00110. And the problem can be represented as a DFA with two states, even or odd. And one way to determine the parity is to start at the even state of the DFA, transverse through the DFA character by character, and report the final state. And therefore the run length n is 5, because we have exactly 1, 2, 3, 4, 5 characters processed now in this way. Can be that simple. Now, the other one is, of course, if we have now identified the run length as one characteristic for the task complexity, is the DFA state space size. And now you know why I started this video with a Möbius strip and a climb bottle and a little ant or a little spider going here on this two-dimensional manifold here. This is exactly why. So we come back now in our real application of LLM when we say we want to define something like a task complexity. We have the run length corresponding to the minimum reasoning steps needed to solve the particular task, and the DFA state space size representing here the complexity of the underlying decision space. How complex is it gonna be? Is it gonna be Euclidean or non-Euclidean? What do you think? Yeah, there's this beautiful, real nice idea that shows here Cornell and Stanford. Look, if you have this problem, so we have this particular problem, if we increase the run length of the problem, this simply means we add here another +1 modulo 2, or this means we go from a run length of 4, 1, 2, 3, 4, and the number of state 2, 0, and 1. We go now to a run length of 5, 1, 2, 3, 4, 5, and the number of state 2, 0, and 1. Or we increase the number of the state that the system can be in. So this means now we say here the problem, we extend the problem, and we say, what is 0, 0, 2, 1, modulo 3? So now we do have the run length of 4, but the number of state is now 0, 1, and 2. 0, 1, and 2, and this is the notation. So you see, these are now the underlying simplified DFA models that we're gonna try to understand what is complexity sensitive to. Is it the number of states, or is it the run length? And at the beginning of my video, it is exactly this, no? The run length is, if you want, how many steps my little aunt can move on a Möbius strip. 4, 5, or whatever, or 7 steps on a two-dimensional manifold. Or do we go here for the number of states the system can be in? This is, if you want, a higher dimensional space. So let's have a look. What is the solution to this? Because the study gives us here a clear answer. Here we have it, Cornell University and Harvard University. Critical thinking. Which kind of complexity governs here the optimal reasoning length, especially if we do test time compute scaling with our LLM for our reasoning models, our R1, our O3 models. Published April 2nd, 2025. This was yesterday for me. And again, they discovered here task complexity, measure 1 and measure 2, the run length and the dimensionality. And now they say, you know, all the reasoning tasks that I already showed you here, that there's a particular L star, if you want, discontinuity. Here we have now the same Crooks evaluation, multi-step arithmetic, web of lies, logical deduction, all the benchmarks. And now we say each task can be represented also as a DFA, as an automata. Because we have the number of states this particular benchmark can be in. This is either the maximum depth or the distinct operators, the possible values for this tracking, or the particular size, or the number range, or the number of objects, the number of people, whatever. And the run length, the second characteristic for the complexity, is simply here number of steps or expression depth or whatever. So they identify this for each of their benchmark tasks, and then they looked at this. And here we have the result. How does complexity affect now the critical length? And you know, the critical length is also an indicator for the best solution of our reasoning task. And they have now, and here you have the critical length to the run length, and here you have in the second one the critical length to the number of states. And if you have the correlation, you see the correlation coefficient here is 80 for the run length and just 0.234 if you want the state space size k. So they found, and this is the main result, that the critical length L star of different LLMs correlate strongly with the run length. So in my example at the beginning of this video is how many steps my little aunt can move on the Möbius strip, and not so much the state space size. Our little spider moving now in higher dimensional spaces and developing shortcuts on a topological space. That is the solution space for a given complexity. And you might say, but this is an indirect argument, no? Because this is just a reference here, a correlation between the run length and the critical length. But the critical length does not tell us 100% in a correlation that it has to be the right answer. No? It just tells us it has the right critical length. But we have to fact check that critical length answer. Because I can answer, just a simple example, I can say the result is 42. This might be the correct answer. Or I say the result of adding here the given two integer number as specified here in the query by the user XYZ results in 42. I mean, both answers show the correct result, but have a completely different length in the reasoning. So just the length is not really the perfect indicator here for the correctness, but it is an indicator. So they say now, the authors, this finding is somewhat surprising, as larger state spaces might imply more complex reasoning. And this is what we thought. Yeah? If we thought, hey, we take now a large language model that has, I don't know, instead of 1 billion free trainable parameters, 5 billion free trainable parameters, we can now cope with more complex reasoning tasks. Yeah? And they tell us, however, our results indicate that this form of complexity does not seem to affect the optimal reasoning length. So the dimensionality of a higher dimensional state space for complex reasoning is not the factor that we're looking for. Does not seem to affect the optimal reasoning length. Remember, they are just referring to the optimal reasoning length. And this is an indicator for the correctness of the complex reasoning. And now the interesting question that I have reading this paper, hey, is this restricted only to the Euclidean geometry of spaces? And now you really understand why at the beginning of this video, I've chosen here some non-Euclidean topological spaces. And then they do something that this is for me the main result, but please read the study yourself. They go on and tell us now one possible hypothesis for this phenomenon is that an LLM may be relying on shortcuts to represent here this automata rather than explicitly representing it in full. So this topic of the LLM doing shortcuts internally, even for a simplified representation of a finite state automaton, this is now an absolute fascinating topic for me, but this is not the main part of the study. So I will talk about this in my next videos. So beautiful. They give us here the GitHub repo, the critical thinking. They have here everything, all the different code and everything that you need is available for you. Beautiful, thank you. But let's come here to an end and let's reflect what we learned about reasoning. You can say, we know nothing about reasoning. My goodness, this is a complex topic. We have no idea how it works, why it's providing some data. So we are just trying out empirically. Yes, absolutely. However, the authors state that together our results are consistent with the hypothesis that additional reasoning token in the test time compute support implicit state tracking, which measured by the run length, as we just showed you, rather than for representing more complex DFA, as measured here by the number of state dimensionality of the space. This is now an interesting statement. Huh? Additional reasoning tokens support here implicit state tracking measured by the run length. So this would mean, in theory, if we have all the implications that are officially shown and inherently hidden, that we can use a lower dimensional LLM if we just give it here more multi-step reasoning capability. We don't need to build a higher complexity in a higher dimensional state that represents the system. But is this really true? They tell us there's a strong correlation here of the perfect length L star with a probability of the correctness. So you see, now we are going back to the probability of the correctness, but it's a beautiful study. Please read it yourself. And they now argue now if LLM best performance at 90% accuracy occurs around 50 token of the reasoning, then the solution with a 10 token string are likely too short. Solution with 150 token in the reasoning might be too long. So we filter out, if we know where for our model the L star, the perfect length of the reasoning token is, we can filter only those solutions that are generated here during the test time. So language models sometimes override here correct intermediate conclusion if they continue to generate here reasoning tokens. This is correct, this is what we know, or they just might fail to elaborate enough if they stop too soon. Absolutely. Underthinking, overthinking. This is the topic of my last videos. And now they come to the conclusion by restricting here the test time compute scaling to an optimal zone. They kind of hope to strip out those overshooting and undershooting errors because they have the wrong length of the reasoning token sequence. I don't know if only the length of a reasoning token sequence will give you a confidential signal on the correctness of the sequence of the reasoning token, because I want a correct answer. So you see, we are trying to find solution, and it is not simple at all. But let's come to a result from this study here by Stanford and Cornell. Here you see it. Summarizes here the accuracy improvement resulting from filtering now the reasoning chains by the predicted optimal length. So you see here accuracy old and here the accuracy new that is now filtered, and the differences we achieve, you have here this either in numerical data or here in a graph, and you see for the different models you achieve different improvements in the accuracy of the reasoning chain. So you see what is the best one. I think the best one is 3.8. So this is here the distilled R1. Then we have plus 3.7% performance improved. This is a Keyon 2.532b. But in general, if you see, we are here in single digit. Now this from 0.0, okay, to 3.8. Where is it? 3.8. This is, or if you see this here, yeah, there's a little jump, you know, there's a little jump for all this model, depending on the model. But is this really the solution to improve here the reasoning accuracy? We go max to 3.8%, and this is not really the solution. This is maybe an indicator that here the perfect reasoning length exists, and we should somehow take care about it. But is it the main indicator? I personally have my doubts. Yeah, the author tells the accuracy improvement resulting from filtering now the reasoning chains by predicted optimal length, and they can now improve here the accuracy of the models here for up to 3.8%. Yeah, and the filtering, as I told you, is done during the inference time. We're here test time compute, not at the training time. So this filter out chain of thought length is simply too far. Then the predicted optimal length. And of course, this is different for every system, for every LLM size, for every LLM that was generated by different corporations. So this is here an absolute specific optimal length of your LLM. So, and they come to the conclusion that along this line of research, tracking here the reasoning length during the training, now the training phase, could potentially serve as a useful diagnostic signal indicating that the training process has now come to the optimum, or the task mastery is now performing at the optimum. I understand the idea that you say we have examined this, and from the test time compute scaling, we understood that the reasoning length has an influence here up to 3.8% for the accuracy of the complete model. And if we go now from the test time compute to the training time, you know, the supervised fine-tuning and the reinforcement learning, if we dare track now here the reasoning length in the training phase, not in the test time compute phase, this could also improve. Yeah, I see this argument, but honestly, I'm personally not really convinced. And I told you about here the different topology here of the search space, of the solution space, non-Euclidean space. There are so many open questions, you know. And I thought that we are a step further with understanding the reasoning of large language model. But especially if we look here at test time compute, multi-token or reasoning models, we have no idea what's going on and how they come to this conclusion. But in my next video, we will have a different view also on the reasoning of LLMs and what other researchers found out. And then we try to solve the puzzle, at least the puzzle pieces that we can put together. And yeah, if you're interested, why not subscribe to this channel? And I'll see you in my next video.